Hi everyone. So today I'm going to teach you about how a recurrent neural network works. So before begin this tutorial, I assume that you already have the knowledge about the traditional neural networks. So if you know how these traditional neural networks are working only, you will be able to understand this neural network type better. So if you don't have any knowledge regarding the traditional neural networks in deep learning, uh, please go and refer some tutorials online, and after that come back to this lesson, and you will be able to understand this much better. So without further ado, let's start our tutorial. So let's see what these recurrent neural networks are. So a recurrent neural networks is a type of neural network that has memory. It doesn't just look at the current input but also remembers what came before to make better predictions. So in simple words, uh, in a recurrent neural network, it will not predict predict something by looking at the current input only. It will predict something by looking at the current input as well as the previous inputs. So it always has that bridge between the present and the past. So to match that, we have developed a special kind of neural networks that is called RNN, or the recurrent neural networks, right? So before going into some complex things, let's see what are the usages in recurrent neural networks. Usages, right? So recurrent neural networks are used in many areas. As an example, text prediction, text prediction, text prediction. It was and also auto completions, auto completion, text, and speech recognition, and what else? Music generation, identifying videos, and weather forecasting. So likewise, there are many usages in recurrent neural networks. So not only one. So as you can see in all of these examples, you can see these data are sequential. So every data, we cannot predict something by looking at only the current chunk of data. As an example, if we take weather forecast, we can't forecast anything by looking at the current input only, because we need to look at all the data in the past, and then only we will be able to predict. And same as speech and videos also same, because in videos also uh, we cannot identify some kind of video by looking at only one frame of that video. We need to analyze all the frames and decide whether this video is related to something or not, right? So that's the concept behind that. So let's go, or let's see a good example that you will be able to grasp this concept, right? So I prefer this example because using this example you will be able to understand this concept much better. Okay, right. So my example is this, right? So I hope you already know feed-forward neural networks, which is the traditional one. So in image classification, let's say that you give the network a single photo of a cat, right? Single photo of a cat, right? A feed-forward neural network can correctly say that this is a cat. Okay, so if we give a single photo of a cat to a FNN network, single photo of a cat, then it can predict whether this is a cat or not. Right, so it can predict whether that is this is a cat or not, because one image has all the information inside it. Because if we feed cats, dogs and other animals to the neural network, so that one image contains all the data which is enough to classify that particular image type. So this scenario will work. But if we try to understand videos using shall we try understand a video using FNN, it will fail, right? It will fail. The reason is imagine you want this network to recognize what action is happening in a video clip, right? This is the video, right? Person is running, right? Person is running, so we want to identify the action in the video, right? So we want to identify the action. So if we want to look at the action, looking at just one frame isn't enough, right? So as you know, video is a series of frames, right? Series of photo frames. If we look at only one photo frame, can we identify what is this video about? We can't, right? We need to analyze all these video frames, right? All these photo frames to predict about what this video is all about, right? So to do this, we need recurrent neural networks, right? So that's where we need a recurrent neural network. So why we use RNN? The reason is RNN process the frames one by one and keep a memory of what happened earlier, right? So RNN always have a memory inside the neural network, right? So it always has a memory, right? So this memory is about the past data. So that's what you need to remember. So I hope you already know the traditional neural networks. That's why I ask you to first watch some tutorials about traditional neural networks. So this memory is related to past data, right? Not the current frame or the current data. So this is related to past data, right? So this memory contains some information about the past data. So it will influence the output of this neural network, right? I hope you will get this. So if you have any questions regarding this, please do ask in the comment section of my video. Right. Okay. Now let's see how this how this recurrent neural network works works in a very simple. Let's see how this kind of recurrent neural network is working inside, how everything is happening inside, right? So to explain that, I'm taking a very small example, right? It's like a very baby example, but you will be able to understand this, right? So uh, let's see what's really happening inside of a RNN network, right? Let's see what's really happening inside of a RNN network. Okay, so suppose that we have this data, right? We have input, we will say it as X, and the output we will say as Y. Okay, so let's say the inputs are 1, 2, 3, 4, 5 likewise, and the output will be 1 plus 2, 3, 2 plus 3, 5, 3 plus 4, 7, 4 plus 5, 9. So as you can see, every output, right, every output in this neural network is not based on this number 2, right, or the not based on the current input, but this has some information in the previous input as well. So to map and identify such a pattern using a neural network, the best way to, or the best neural network that we should use is a RNN network. Okay, so that's the best neural network. So using this kind of neural network, the network will be able to learn this pattern very quickly and efficiently, right? Okay, now let's write this thing again in a proper way. X equal 1, 2, 3, 4, 5. Y equal 3, 5, 7, 9. So this will go on and on, right? Okay, now to understand this better, right, to understand this better, we are going to draw a small neural network, right? Let's draw a very small neural network. and this will be a RNN network, right? So before I draw that, let's say I will explain about this neural network that I am going to draw, right? So this neural network have one input, okay, one input neuron, right? One hidden layer neuron and one output neuron, okay. So and we have these parameters in this neural network: weight of x, right? It will be 0.5. that means input to hidden, okay. Weight of hidden state, right? Don't think too much about this. I will explain it later after this thing. And the weight of y, that means the output layer, right? This is the output layer's weight, initial weight, right? All right. Now let's draw the neural network. So in traditional neural network, right? So this will be my input layer, right? And this is the hidden neuron that I told you, and this is the output neuron, okay. So here the weight is 0.5 and here the weight is 0.8, right? So as you can see, in this neural network, if we input something, say for an example, if I input number 1, then it will go through this weight 0.5, and for now let's assume that we don't have any activation function, no activation function in this hidden layer. Just for the simplicity, let's forget about these activation functions, right? Our input will go through this 0.5, and after that it will go through this 0.8 weight, right? And it will do some prediction. But in order to map the or in order to remember the past data, we are introducing a new weight called hidden weight, right? So in RNN network, we call this neuron as a hidden state, right? Okay, so there will be another weight. That weight is called hidden state weight of hidden state. Let's assume weight of hidden state is 0.1, right? So whenever new value is passed, it will go through this, and also it will go through this hidden weight, and after that only it will go through this weight y, right? So in here hidden weight will get updated uh, with the previous information as well, with the influence of previous information as well. So let's see how this really happens after this. Okay. So now let's do a dry run, right? So as you know, in a neural network we need to do a forward pass first of all. So let's run a small forward pass, right? So in here I'm more focusing on this hidden state, right? This one, right? In below explanation, I'm more focusing on this hidden state. So we process the sequence one time step at a time. Okay, we are processing this sequence one time step at a time. Give me a second. Right. So let's see. So hidden state, we are taking the weight of input and we multiply it by the time step plus weight of hidden state into h t minus 1, right? So this will be the formula. So let's see what does this mean, what is meant by this formula, right? So in recurrent neural networks, right? So suppose we have these data, right? So these are the inputs. We call these inputs as time steps, right? Time step 1, time step 2, time step 3, time step 4, time step 5. So likewise we call these inputs as a time step. So we pass each input one by one, right? So that's why we say, so when we are explaining this, we say at t equal 1 and input 1 is 1. So this means at time step 1 the input is 1, right? So at that time so hidden state at time step 1 is, so as you can see, when an input is coming through the x, it will first go through this 0.58. So let's say 0.5 into, so what's the input? This is the input. So our input is number 1. Then we need to add, then only after here only it will go through this route, through this weight. So that weight is 0.1, 0.1, right? And it will be multiplied by the previous weight. Okay, so not the previous weight, previous hidden state, right? So since at input 1 there is no, right? Here you can see there is no output, right, in number 1. So that means previous hidden state is 0, so we'll put 0, right? And the output of that at time step 1, the output of the hidden state is 0.5, right? Now we have successfully updated this ht at t1. We have successfully updated, and now we are slowly reaching this part. Now the output will go through this output layer, through the output layer's weight, and it will give the prediction, right? So let's see the prediction. y1 prediction equals 0.8 multiplied by 0.5, the hidden state, right? So this came from the hidden state. Remember, this is not a weight, right? This is not a weight. This is some kind of value which represents the past data, right? This represents past plus present data. We multiply it and we get a output which is 0.4. So at the first pass our prediction is 0.4. So likewise we can repeat the same step for time step 2. As well. So if I quickly do that calculation here, it will be h2, so 0.5 into 2. Why this is 2? Because this time our input is 2. Okay, it's coming from here, and plus 0.1. 0.1 is the weight of this hidden state. 0.1 into 0.5. So remember, now I am going to multiply it by 0.5. Last time we multiplied it by 0 because we didn't have any past data, something telling something about past data. But now we have some kind of variable which is telling about past data, right? So that's why we are going to multiply that weight by this 0.5. Okay, so the answer will be 1 plus 0.05 equal 1.05. So this is at time step 2, right? So likewise, if I draw if I take the time step 3 as well, x3 equal 3, if we take the time step 3 as well, in time step 3, let's do the quick math. 0.5 into 3. Why 3? Because the input is 3 plus 0.1 into 1.05. So where does that came from? It came from the previous hidden state, right? So this reflects past plus present data, right? Some kind of representation between the past and the present, right? And the answer is 1.605. Okay. Okay, before that, I forgot one step. At time step 2, so after we calculate the prediction, we need to calculate the prediction of y2. So y2 prediction is 0.8 into 1.05, which is 0.84, and we need to calculate the loss, right? So as you know, in every neural network we need to calculate the loss, right? So that is common in here also, the loss function, right? For now I'll delete this T3 part. For now I'll delete this T3 part, and we need to calculate the loss. So the prediction is 0.85. Then before I calculate the loss, you might think why we are not calculating the loss for T1, because there's no loss at T1. We are starting comparing at T2, right? Because since this is RNN network, so we are usually starting it with T2 in this example, right? So let's start calculating loss. So the loss of time step 2 will be 3 minus 0.84. Wait, I'll need a calculator to calculate this. 0.3 minus 4.6656, right? So this will be the loss. So where does this 3 came from? 3 came from our output parameter. So as you can see, at time step 1 we input 1, but there will be no output. At the time step 2 we have inputted 2 and the output was 3. So this is that 3. Okay, this is that 3. So this tells our loss is 4.6656. So if we do not take the square root, actually as I remember, this is called error, right? So if we remove this, it says that we are if we take this part only, .16, yeah, right. So this is the loss, right? Now let's come to the time step 3, T3, and x 3 equal 3. So in here also we are doing the same. Why 3? Because the input is 3. Zero 0.1 into 1.05. So I already explained where this 1.05 came from here. So this representation has past plus present information, and this 1.5 plus 0.105 equal 1.605. So the prediction is 0.8 into 1.605, which is wait, one point 284. And let's calculate the loss in here as well. So at time step 3, the output is 5, right? So 5 minus current prediction is 1284. Let's say the answer of this 5 minus 1.284, 1.284, 3.716. So this will be the loss at time step 3. So likewise we can do this for, so in a real neural network this calculation is going like this way for all the inputs. Then so as you can see in my calculation, you can see at different stages the hidden state had different values, right? 0.5, 1.05, and this hidden state had 1.605. So likewise these hidden states had different values. So whenever a new input is coming, for the calculation, for the forward pass calculation, yes, of course we are only considering about the 1.065 value in the hidden state. But in a real neural network, it keeps track of all these hidden states in a separate table. It's like a table, right? How can I show you? Let's draw a table like this. This is the hidden state. Y. Prediction. And the target. So in array or something like that, in the program of the neural network, they keep each these hidden states. So the reason for that is, even though we don't need all those data for forward pass, we will later need it for in the back propagation step, right? Which is the back propagation through time for these RNN networks. So to do that, we need all those past data, right? So we maintain one. So at time step 1, time step 2, time step 3. So likewise, it will go on and on. So since we have calculated only up to time step 3, let's put the input values for these time steps. That's also 1, 2, 3. So it could be any number, but in our example, it is 1, 2, 3. And the hidden state at those steps were, at the first time step, the hidden state was 0.5. At the second time step, the hidden state was 0.5. Third, 1.605. And the prediction was 0.4, 0.84, 1.284. First one, we didn't have a target because there's no output. Second one, there's a target. Which target means the output, right? So this value. And the third one, 5. All right. So we have successfully done a forward pass. So I hope you already understand how this past information will influence the present output, right, in this forward pass. So once we have done this forward pass, the next step that we are coming is back propagation. Right. BPTT. So in here, back propagation, what we do is we are adjusting the weights, right? We are adjusting the weights based on the predicted value, right? So what we are doing in recurrent neural networks is there could be scenarios where in normal traditional neural networks we forward pass one input, and after that we will do a back propagation, and we will adjust the weights. So that's how we will do it in a traditional neural network. So the same concepts apply for these RNN networks as well. So I'm not going to focus too much about the back propagation steps because that's almost like same concepts in here. What I wanted to highlight in this tutorial is how this relationship between the previous data and current data is built in a network. So I think with this explanation you already know that. Anyway, I'll do some back propagation steps very quickly. So if you need any explanations about these steps, please feel free to comment below. I will try my best to respond them. Okay, let's quickly go through these back propagation steps. Back propagation, BPTT, right? So at t equals 3, that means time step 3, because remember in back propagation we always start from the end to the first thing, right? So in the neural network also we start from the output layer, right? So in here at t3 1.285 1.284 minus 5 minus 3.716. So this is the error. Okay, this is the output error at t3. Output error, this is the output error. And now let's see hidden to output weight update, right? Hidden to output weight update. So it will be minus 3.716, which is coming from here, into 1.605 equals. So I already have these numbers written in a piece of paper for my ease of doing the video. So I'm not going to use calculator or anything here. Minus 5.964, right? Otherwise you might think how I'm doing these calculations so fast, right? Okay, then after that let's see error passed into hidden neuron, right? So error passed into hidden neuron, this part. So error was 3.716 into 0.8, which is minus 2.973. Okay, and now let's see previous hidden current hidden weight update. So in here what we do is we take this number, error passed into the hidden neuron, right? So it is minus 2.973. So because at this stage this part is receiving that number, right? This part is receiving that number, so we take that number and we will multiply it by the previous hidden state's value, because at that stage the current hidden state state value is not valid because it was not updated, so we need to take the previous one. So 1.05. If you look at the table, you can see this is 1.05 and it's equal to minus 3.121. And again let's calculate input to hidden weight update. So input to hidden weight, which means this part, okay, this part. So we always look at the input value in here. So in here minus 2.973, which is this value, into 3 minus 8.919. okay, so you can see in here when we look at the values, you can see at T3 the input at T3 was 3 and the Wx, right? So Wx means the weight in the x has played a big role for this error, so it has a bigger number, as you can see. Okay, so likewise let's calculate the same things for at time step 2 as well. At t equals 2, so let's calculate the output error. dy2 0.84 minus 3 minus 16, right? So as you can see, why I took 0.84, because we have that number, right? 0.84. So while doing this, hope you also understand why we are keeping these records in the neural network program, right? So we need them later for the backpropagation steps. So 0.84, right? 0.84 minus 3, so minus 2.16. so this is the error at T3. okay, so just in case if you are wondering what is this minus 2.16, so that means output was too low by 2.16, right? Now let's see the hidden neuron error. So at the time steps 2, the hidden neuron error is coming from two places: its own output path as well as future hidden state, that means the T3. Because remember, this is backpropagation, right? So in backpropagation we are doing the things in reverse way. So we are somehow trying to figure out what causes the error, right? So here we have its own output path, which is how can I say this, dy2 into weight of y. dy2 into weight of y So which means minus 216 into 0.8, 1.728, right? Yeah, okay. So minus 216 came from here, and the weight of y. So this is its own one, and after that the future hidden state. Future hidden state at t equal 3. So here d h3 into wh so it is, as you can see, dh3 is 2.973, 2.973 minus into weight of x 0.1. So the answer is minus 0.29728. Okay, now we add these two numbers. We are going to add these two numbers, right? And the total is minus 2.025. So can you tell me what this value means? So it means the hidden neural net time step 2 feels a total propagation error of minus 2.025. At time step 2 it feels like a total propagation error of minus 2.025. so if we convert these into words, that's how we can express that, right? Then after that we do the weight updates. Weight update the weight of y will be 2.268. Weight of hidden state 1.0125 minus 4.054. So all links feeding into H2 are corrected in here, right? Give me a minute. So you might be wondering how I get these numbers. So I got these numbers from these, right? Minus 216 into 105 minus 216 is the error at time step 2 into 1.05 came from at time step 2 hidden state value, right? And so this much of contribution was done at this point in the weight of y, right? And this value we have taken by taking minus 2.025 into 2, sorry, into 0.5, and this value I have taken by multiplying minus 2.025 into 2, which is output, sorry, input. So this is the weight update, right? So now hope you have a basic understanding. Now I'll quickly go through the at time step 1 calculation. So in here no direct output yet, because as you can remember, so since this is a recurrent neural network and we are finding a sequential pattern, there's no direct output at this time step, but error flows back from the future hidden state. So remember, so we are doing back propagation, so error flows back from the future hidden state. So therefore dh1, so dh2 total into weight of hidden state, that is minus 2025, right? With this one, okay, this value 2025, and the TWX is minus 0.2025. Even the very first input contributes slightly to the final mistake, so that's what it is, right? And after all these steps, we collect the totals, right? In step 3, collect totals, right? At dwy minus 8.232, dwh minus 4.134, dwx minus 13.171. So actually if we take the meaning of these, so these are the total nudges. So hope you know the meaning nudging. So small tweaks, nudges for these weights, for the weights. And at step 4 we update the weights, right? Updating the weights. So when we are updating weights in a neural network, we are not directly going to update the weights by these numbers, right? So we are always updating the weights by a small proportion, so that is called learning rate, okay? So for this example, let's define the learning rate is learning rate as 0.01, right? Then if we multiply these values by 0.01, we get these outputs. Wx new weight is 0.632. Weight of hidden new will be 0.141. Weight of y new value will be 0.882. So now the model has slightly bigger weights, right? Slightly bigger weights because the gradients were negative, meaning it will try to produce larger outputs next time, because since the predictions were too small before. So that's basically how these recurrent neural networks work. So in practice, since this is a very primary recurrent neural network, in practice we will have a activation function in these neurons, especially in a hidden state. So most common ones are like tan H, likewise. So in such cases we will need to find derivatives as well when we are doing backpropagation kind of things, but for the simplicity I haven't included any of those to this example. So I just want you to explain the concept behind this and how this will link the relationship between previous data. So that was the main idea that I wanted to tell you. So I hope you grab that. Some may not feel comfortable about these backpropagation steps because I quickly went through, because I have written this on a paper, and I have quickly done the calculations likewise, but I have tried somehow to explain each and every step. All right, so that's all about the recurrent neural networks. So if you do like my video, please like my video and subscribe my channel. So if you like my teaching style, please give me a good comment. So that's all about it. Thanks for watching. Have a nice day.